Okay, here we go. Sorry about that fun entrance. This is Precalc video 1, instructional video 1. Today we're talking about simplifying evaluating expressions with exponents and with radicals. Where to find this in the textbook. So in the textbook, if you go all the way to the back of the book, it is in the appendix. So it's A.2, it's page A13. Or if you're on WebAssign, you go to the ebook, you click appendix all the way down at the bottom, and you'll find it in A.2 exponents and radicals. That's what we're talking about today. So on page A13, you will see this property of exponent rules. It's right there. I'm not going to write them all up here on the board. Those are things that in Precalc we kind of expect you to know most of those. As it is, what we're going to do today on the video is we're going to go over some examples applying these rules, and we'll talk about them as we go. So let me get my presentation here. So I'm looking at my computer while I'm doing this, so I know what I'm supposed to be talking about. So we're just going to do a few examples with evaluating and simplifying. So let's say we want to evaluate. We have 4 to the third times 4 to the 5th over 4 to the 10th. Now remember, an exponent, right? This is an exponent. The 5, the 3, and the 10 are all exponents. Those imply repetitive multiplication. The big number, the bottom left corner, that is the base, and that's the number that's getting multiplied over and over again. So here we have 4 times 4 times 4, 3 of them. 4 times 4 times 4 times 4 times 4, 5 of them. Those multiplied together. So if I have 3 of them multiplied together and I got 5 of them multiplied together, how many do we have multiplied together? You're right, we have 8. We have 8 of them. So in the numerator here, really we have 4 to the 8. And you'll see, what do we do with those exponents? If we have same base, 4 to the third, 4 to the 5th, multiplied together, we can add those exponents because we're counting how many we have. Still, we just have 4 to the 10th down here. So what we have here now is we have 4 times 4 times 4, 8 of them up there. 4 times 4 times 4 times 4 times 4, 10 of them down here. Now, if I have multiplication in the top of the fraction, multiplication in the bottom, so multiplication numerator, multiplication denominator, 4 over 4 cancels. That's 1. That's 1, right? 4 divided by 4 is 1 times 4 over 4 is 1. How many of these can we cancel out? Well, there's 8 multiplied on top, there's 10 multiplied on bottom. So here we can cancel out 8, and we're left with 2 in the denominator. So here this is equal to 1 over 4 squared, which is 1 over 16. 1/16 is our answer. And the reason why the 16 or the 4 squared is on the bottom is because the bigger exponent is in the denominator. Cool. Let's do another example. This time it's a little bit more complicated. So we've got 2x to the third, x's, times 4x y to the 5th divided by 5x squared y to the third times 2x to the negative 4th. Okay, look at that. So in your homework and stuff, I'm not going to give you a problem quite this complicated, but I'm going to do this problem here in this example because really it's a few problems all wrapped in one example. And if you can kind of understand what's going on here, you should be able to do the more easy problems on homework. Okay, so I'm just going to look at this, and first thing I do when I look at this is say, are there any negative exponents? And are there any 0 exponents? Here there are no 0 exponents. Remember, if I have something like this, x to the 0, that equals 1 as long as x is not equal to 0, right? And then here if I have something like this, x to the negative n, that's the same as 1 over x to the n. Remember how I said exponents imply repetitive multiplication? Well, that's for positive exponents. So if I have like x squared, it's x times x, right? So that exponent is saying how many times do we multiply? Well, if I do the opposite of a positive exponent, a negative exponent, we gotta do the opposite of multiplication, which is division. So here I've got this x to the negative 4th in the denominator. So here it's this right here, this x to the negative fourth, is like 1 divided by x to the fourth. So we got a double division going on here, so basically that x to the negative fourth, anytime you have this, it's just that, is what I'm trying to get at here. That negative exponent, in order to make it a positive exponent, you move it to the top of the fraction, or sorry, you move it to the other side of the fraction bar. So the first thing I'm going to do is I'm going to take this x to the negative fourth, and I'm going to move it up to the top of the fraction as x to the positive fourth. So now, just 2x to the third, 4x, y to the fifth, x to the fourth, over 5x squared, y to the third times 2. Now what I'm going to do is I'm going to basically combine like factors. They're not like terms because they're being multiplied, like terms when we're adding or subtracting. Here they're like factors. So I'm saying, well, I've got these numbers in the numerator, 2 and 4, and those are being multiplied because it's all multiplication here. So I'm just going to, what's 2 times 4? It's 8. So I'm going to write an 8 in the numerator. All right, I go 2 times 4, combine those, that gives me an 8. Now I'm going to look and say, oh, check it out. There's an x to the third, there's an x, which is x to the first, and there's an x to the fourth. So I'm going to say, how many x's are being multiplied in the numerator? 3 plus 1 is 4, and I got 4 more there is 8. So here I have 8x to the 8. Notice how these 8's came from different things. I multiplied 2 and 4 because those are base numbers, or regular numbers being multiplied. This 8, this exponent, came from combining all the x's. We had 8 total x's being multiplied. Now we got a y to the fifth. There's only one y thing there. It's just y to the fifth. So we just write y to the fifth. Ew, that's a 5. It doesn't look like it, but it is. Promise. Now I look down at the denominators. Oh, it's a 5 and a 2. Those, remember, are being multiplied, so that's 10. So here I have 10, and then x squared, y to the third, because there's no other x's, y's. Now what we're going to do is we're going to simplify that fraction, that rational expression. So I have 8 over 10. We can factor 2 out of each of those and get 4/5. You could have also realized here, like, oh, check it out. I got a 2 in the numerator, 2 in the denominator. Cancel those out, get 4 over 5. So 4/5, 4 in the numerator, 5 in the denominator, from canceling that. Or, sorry, simplifying, not canceling, simplifying that. Now I look at my x's. I have x to the 8 divided by x squared. So I have 8 x's in the numerator being multiplied. I got 2 in the denominator. I would cancel out 2 of them and be left with 6 in the numerator. So I have x to the 6th in the numerator. And then here, I have y to the 5th divided by y to the 3rd. 5 y's multiplied on top, 3 y's multiplied on the bottom, 2 left over, and they're going to be on the top. So here I have 4x to the 6th, y to the 2nd, over just 5. And that would be the simplified answer there. Okay, one more problem, and then we're good to go for exponents. Okay, so this one is, we have 24, I'm going to draw a line here, 24x to the 3rd divided by 18x to the 7th y squared. And then I'm going to put that all to the negative 3rd. Okay. So with this parentheses, like this thing, to a power, what happens is this negative 3rd exponent is going to apply to everything inside that group, inside those parentheses on that fraction. So what I'm going to do is I'm going to look at this 3rd power in 2 ways. Or this negative 3rd power, I'm going to look at it as a negative and as a 3rd power. First, I'm going to deal with the negative part, because we all know this is true, right? Negative 3 is just negative 1 times 3. So I'm just going to look at the negative 1 part of it. And what does a negative exponent do? It flips it. It takes anything in the denominator with a negative exponent, to make it a positive exponent, it's going to go to the numerator. Anything in the numerator with a negative exponent, to make it a positive exponent, goes in the denominator. So a negative exponent, like a something to the negative 1, if I have something like this, a over b to the negative 1, It's b over a. It's kind of, it makes it a reciprocal, flips it. So what I'm going to do is I'm going to rewrite this as the reciprocal with a positive 3 as the exponent. So I'm just going to flip it, everything in the denominator, 18x to the 7th, y to the 3rd, is going to be now in the numerator, and everything in the numerator is now going to be in the denominator, and I'm going to make this a positive 3. So what I did is I applied the negative part of this exponent to everything in here. Wait, now you'd be like, all right, what's 18 to the 3rd? What's 24 to the 3rd? I mean, I don't know. I got a calculator right there, but I'd rather not use it. What we can do is we can simplify that. We can simplify inside this fraction and then apply the 3 as an exponent. You could apply the 3 as an exponent to everything in there and then simplify after if you want. But I think it's easier to simplify inside and then apply the exponent. So we're going to do that. We're going to go 18 over 4. What's 18 over 4? Or 24. Sorry, not 4, 24. So we got 18 divided by 24. And we're not going to like plug that in and get decimal. No, we're going to write it as a fraction. And you may or may not have one of these fun yellow fractions with this, or yellow fractions, yellow calculators, with a fraction button right there. If you do, I mean, I guess you can use it, but we can use our brains. We're like, what number divides into 18 that also divides into 24? Well, we got like 2, we got 3. 2 and 3 both work, so 6 works. Anything bigger than 6 going to both of them? No. So I can rewrite this as 3 times 6. I can rewrite this as 4 times 6. Cancel the 6's. 18 over 24 is the same as 3/4. It's the same as like dividing this by 6 and dividing that by 6. So here I have 3 over 4. What I did right there is I simplified the stuff with the numbers. Simplified that. Now I'm going to simplify my x's. I have x to the 7th over x to the 3rd. Right, remember what we were doing over here? Basically what's happening is we're subtracting the exponents here. I've got 7x's, I've got 3x's, 7 minus 3 is 4. Or think of like 7 on top, 3 on bottom, cancel, you're going to get rid of 3 of them. You're going to be left with 4x to the 4th, x to the 4th from that. And then here there's just a y to the 3rd left over. Don't forget about the 3 right there. Cool. So now what we can do is we can apply that 3 as an exponent. So it's going to come in as an exponent on each of these. So I'm going to get 3 to the 3rd, x to the 4th to the 3rd, y to the 3rd to the 3rd, over 4 to the 3rd. And like, oh, that's a terrible answer, Mr. Race. You're right, that is not a good answer. That's not what we want. But I'm getting there. So 3 to the 3rd, that's 3 times 3 times 3, which is 27. 3 times 3 is 9. 9 times 3 is 27. So I'm going to go up. This is getting kind of weird. So I have 27. And then here I have x to the 4th to the 3rd. So I have x to the 4th times x to the 4th times x to the 4th. I have 3 x to the 4ths. So each x to the 4th, right? X to the 4th times x to the 4th times x to the 4th. Well, there's 4 x's multiplied, 4 x's multiplied, 4 x's multiplied. There's a total of 12 x's that are being multiplied there. Anytime you have a power to a power, you can multiply those powers. So here I have 27x to the 12th. And then here I have y to the 3rd to the 3rd. So it's the same idea here. It's y to the 3rd times y to the 3rd times y to the 3rd. How many total y's being multiplied there? We got 3 of them, 3 of them, 3 of them. We have a total of 9 of them being multiplied. So here, y to the 9th. And then over 4 to the 3rd is 4 times 4 times 4 again. So 4 times 4 is 16. 16 times 4 is 64. And that's our final answer for that. Wonderful. Okay. So once again, these are kind of complicated problems. And if they're like a little bit out of your comfort range, that's okay. Try the homework anyway. And right now, after these examples, you should be able to do problems 1 through 10 on the homework. I'm assuming that WebAssign didn't mix it up. I'm still getting to know WebAssign a little bit. But you should be able to do those. They're more simpler than these problems. These were just to get all the different rules in there, hopefully. All right, so now we're going to move on to radicals. Now, a radical is like totally radical. I'm just going to like erase for a bit. And I apologize if this like makes that noise when I write on it and stuff. Sorry. Okay, radicals. So this is a radical symbol. Let me make sure it's lined up the way I have it in my notes. So this is the same as a to the m over n. The nth root of a to the m is the same as a to the m over n. An nth root or a radical is just a rational or fraction exponent. So if I had this, the nth root of just a, it's the same as a to the 1 over n. So you know all of our properties from that page A13 that I like went like this, that I went like this with? Cool effects, right? So all those properties still apply, but now it's just written differently. Okay, and you'll see a bunch of fun properties further on in this. It's like on page A18 in the book. You just like scroll down or go over in the web assign, you'll find them. But we're gonna do a few examples to give you an idea of how to do the last couple of homework problems on the homework assignment, and then you'll be ready to go. Hopefully this isn't too long for you. Okay, first problem, we have the square root of 75x squared. Now, here, notice this is an nth root. Anytime you don't see a number, which is called the index there, it's implied that it's the square root, because the square root is like the most common root that you take. All right, so here it's the square root of 75x squared. It's basically what it is it's 75x squared to the 1/2 exponent. That's what it's saying. So we've got this property of like this stuff in these imaginary parentheses to the 1/2 power. Both those things are getting square rooted. So what I'm gonna do is I'm gonna square root that 75, then I'm gonna square root that x squared, and I'm gonna write my answer out. And this is gonna be a little different than you probably learned it in Algebra 1 and Algebra 2, but don't worry. Well, the 75 will be fine, you'll be good there. So I'm gonna square root the 75, and guess what? I'm not really gonna use my calculator for this. And I'm gonna square root the x squared. All right. So square root of 75, what we're doing here is saying, well, it's not a nice number. If you plug it in, you're going to get an irrational number. Irrational, it's with an I. Not an E, I made it sound like it was an E. You get an irrational number, we don't really like to write those out because those decimal approximations go on forever, like pi. So what we do is we say, hey, is there a perfect square living in 75 as a factor? In other words, any of these, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, da, da, da. Those are all our perfect squares. If any of these are factors, or like divide nicely into 75, then we can factor that out and square root it. So what we do is say, hey, check it out. 75 is 25 times 3, right? Because 3 quarters, right? Like the little pieces of metal that you buy things with, those quarters, right? 3 of those make 75 cents. So 3 times 25 is 75. So square root of 25, that's just 5. So here we have 5, we say 5 root 3. It's 5 times the square root of 3. That's what square root of 75 is. All right, now we're like, hey, square root of x squared, that is, say it, what is it? You want to say this, right? You want to be like, that's x, because the square root and a square undo each other, right? But we call this the principal square root. In other words, this only gives positive number answers. And I misspoke there, or 0. It could give you 0 as well, so it should be non-negative answers, not positive. My bad. Not going to edit it though, because this is learning. We got to correct ourselves as we go. So what we got to do is say, well, it's only going to be positive. Like if this is a -2 and I square it, I get 4, and I square root 4. What's the square root of 4? It's 2. So basically what happens is a negative 2 turns into a 2. What thing like takes a negative number and makes it a positive number? Absolute value. Absolute value. So here, the square root of something squared is the absolute value of that thing. So here I have 5 absolute value x times the square root of 3, or you write it as 5 root 3 times the absolute value of x. That would be our answer there. So anytime if you have the nth root of a to the n, and n is even, as in 2, 4, 6, 8, and so on, this is equal to the absolute value of a. Because those principal square roots for real numbers only give non-negative answers. Like if you square root 100, you get 10. Now this is different than, I know some of you are probably like, wait, what about the plus minus square root? That's different. That's when we're using the square root as an operation while solving. If we're using it while solving and we're trying to find solutions, there are two numbers that you can square to get 10, or sorry, to get 100, 10 or negative 10. But when you square root 10, you get just, square root 100, my goodness, you square root 100, you just get 10. Okay, so that's why we got to go absolute value of a. Because you could take a negative 10, square it, get 100, and then square root the 100 and get a positive 10. If it's odd, if you have like this, if n is odd, don't worry about it, you just get a. Because like the cube root of negative 8 is negative 2. It gives you a negative number, so don't worry about it. All right, cool. Let's do some more examples after that little bit. And this, we'll see this again. Oh, right. I'm gonna keep this up. That's gonna stay. This isn't. And remember, you're watching a video on YouTube, right? So if you're like, oh, Miss Grace going too fast, just pause it. Or, take that little bar at the bottom and like scroll it back. Right? You got that power. That's like maybe one of the few benefits of this remote learning thing. All right. So we've got the cube root of 16x squared. Sorry, 16x to the third. Oh my goodness. Let me read it first before I say it. 16x to the sixth. There it is. Over 27. All right, so once again, this is like a 1/3 power because it's a cube root. So it's this fraction, this rational expression to an exponent. We can bring that exponent and apply it to everything, or bring that cube root and apply it to each individual factor. So I'm going to cube root the 16. I'm going to cube root the x to the 6th. I'm going to cube root the 27. All right, the cube root, let's start with the easy stuff first. Cube root of x to the 6th, this is like x to the 6th to the 1/3. What's a third times 6? Well, it's 6 over 3, which is just 2. Sweet. So we get x squared. All right, cube root of 27. Well, we know 3 times 3 is 9, times 3 again is 27, so it's just 3. Because, right, the cube root of 27 equals 3, because 3 to the third is 27, right? So now we're looking at that 16, and we're like, 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. There's no nice number, like whole number, that we can cube and get 16. So what we do is we do something similar to what we did here with that 75. We say, is there a perfect cube that lives inside the factors of 16? And yes, 2 times 2 times 2 is 8. So 2 to the third is 8, right? And 8 times 2 is 16. So what I can do is I can rewrite this, I can rethink this cube root of 16 as the cube root of 8 times the cube root of 2. And the cube root of 8 is just 2. So it's 2 cube roots of 2 times x squared over 3. So this cube root of 16 is 2 times the cube root of 2. Okay? And we got that by basically, another way to do this, you're like, Mr. Race, this doesn't make any sense at all. Just break this down. Say like, hey, 16 is 4 times 4. Each 4 is 2 times 2. Check it out. We have 3 2's being multiplied there. That means 2 to the third goes into 16. So I could take this 2 to the third and cube root it and get a 2. And I got 1 2 left over. That goes back inside the cube root. We didn't get to bring that out. We didn't simplify that part. Okay, so this is the answer to that. Sorry for all the arrows. One more problem, and then that's it for the video. I have no idea how long this is taking. This is kind of crazy. I haven't taught in a while. All right, so now we're going to go square root of 24, x to the third, y to the fourth. Now, I want you to pause the video and try this problem. So, like pause, try it. If you already paused and tried it, and I'm still talking about pausing it, I apologize. Okay, so hopefully you paused it, hopefully you tried it. Now we're gonna go over it. All right, so we're gonna break this up and be like, all right, this is like something to the 1/2 power, so I can apply that 1/2 power, or that square root to each thing being multiplied. So I can say, oh, square root of 24. I don't know why I have 2 purple pens in my hand. Square root of 24. Say, are there any perfect squares that are factors of 24? We're gonna look at our perfect squares. We're like, well, do any of these divide into 24 nicely? 4 does, right? 4. So I can say 24 is 4 times 6. So when I square root that, it's square root of 4 times square root of 6, which is 2 square roots of 6. So 2 square roots of 6. That's what I get when I simplify the square root of 24. And then I'm like, all right, so let's square root this x to the third. Like, ooh, are there any perfect squares that live inside of x to the third? Well, yeah, x to the third is x squared times x, right? So what we get here is, if I square root, we get absolute value of x times the square root of x. Now, this is a little bit tricky here. You ready? Do we need this absolute value of x? And the answer here is no. We don't actually need it, because if I have a negative number for x, and I'm only dealing with real numbers, let's say, then x times x times x, if it's negative, it's going to be negative. I'm going to be square rooting a negative. And we'll get an imaginary number from that. So here we can leave out that absolute value because we still have an x in the square root, so we don't have to worry about it. Okay, I mean, if you keep that absolute value in there, it's still good with my standards. I'm not sure how WebAssign will give it to you, but you get multiple attempts on WebAssign before it locks you down, so you can try it with the absolute value, try it without if you're not quite sure. All right, so here we have x times the square root of x. And then lastly, I've got the square root of y to the fourth. Now, square root of y to the fourth, well, this is the same as y to the fourth to the 1/2. And remember, if we have power to power, we can multiply them, right? 4 times 1/2 is 2, so it's just y squared. All right, we could also say y to the fourth is y squared times y squared, or y squared squared. So that's why it's y squared that comes out. Now, do I need absolute value around the y squared? Well, let's think about that. Is y squared ever going to give you a negative output if y is a real number? Like a number times itself, is that going to be negative? No, so we don't need the absolute value, once again. So that's it, that's our answer. Hopefully you'll be able to do the last 2 homework assignments, or sorry, last 2 homework problems, and that's it. And hopefully you somewhat, a little bit, enjoyed the video. All right, thanks. Enjoy your homework. I hope I hit pause. Oh, I didn't.